Take a moment and look around you. What do you see? Maybe the clean lines of a table, the gentle curve of a coffee cup, or the flat, solid floor beneath your feet. To our human senses, the world appears remarkably smooth and continuous. Space itself feels like a vast, empty, and unbroken stage where the grand drama of the universe unfolds. This perception of calm, orderly space has served humanity well for centuries. It allowed us to build cities, navigate oceans, and even send rockets to the moon. Our intuition tells us that if we could zoom in, space would just get smoother and more featureless, kind of like looking closer at a perfect sheet of glass. But what if this is all just a grand illusion? What if the serene and stable reality we experience every day is just a convenient simplification? To understand where the idea of quantum foam comes from, we need to visit one of the most bizarre and wonderful pillars of modern science, quantum mechanics. Formulated by Werner Heisenberg, the uncertainty principle tells us something astonishing about reality. It states that you can never know certain pairs of properties about a particle with perfect accuracy at the same time. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. For fleeting moments, pairs of virtual particles can borrow energy from the vacuum, spring into existence, and then annihilate each other, returning the energy before the universe can notice. The Casimir effect demonstrates that this vacuum energy is real. When two uncharged metal plates are placed incredibly close together, they are pushed towards each other by an unseen force. The Planck length is about 1.6 times 10 to the minus 35 meters. If you were to scale up an atom to be the size of the entire observable universe, the Planck length would be roughly the height of a single tree. This is the fundamental pixel size of our universe. At this unimaginably tiny scale, the predictions of quantum mechanics and general relativity collide in spectacular fashion. The smooth rubber sheet of Einstein's theory dissolves into a chaotic, bubbling, ever-changing foam. Quantum foam is the equivalent of molecular chaos, but for space-time itself. In the mid-20th century, one of physics' most creative minds, John Archibald Wheeler, dared to stare into this theoretical abyss. Wheeler started with Heisenberg's uncertainty principle and connected it to Einstein's E equals mc squared. If energy can fluctuate, then mass can fluctuate too. And according to general relativity, mass and energy tell space-time how to curve. Wheeler envisioned a landscape where the geometry of space and time is constantly warping and bubbling. Tiny wormholes could be forming and pinching off, connecting distant points for infinitesimal moments. In 1955, Wheeler gave this bizarre, dynamic texture of space-time a wonderfully descriptive name: quantum foam. The idea that empty space could contain energy might sound like science fiction. Yet quantum mechanics forces us to abandon this common-sense notion. Even in a perfect vacuum, quantum fields still exist. According to quantum rules, a field cannot be perfectly zero everywhere. These are called quantum fluctuations, the faint residual tremors of the universe. When physicists try to calculate vacuum energy, they arrive at a staggeringly large number. Our observations show the universe expanding at an accelerating rate, but this expansion is driven by dark energy about 120 orders of magnitude weaker than predicted. This discrepancy is famously known as the cosmological constant problem and is one of the biggest mysteries in all of science. At the Planck scale, the very concepts of length and duration lose their clear meaning. The fluctuations of quantum foam would make the geometry of spacetime itself uncertain. If quantum foam causes space-time curvature to fluctuate wildly, then the flow of time itself must also fluctuate. Time would not tick forward smoothly, but would jitter and stutter. This foamy structure would be populated by virtual black holes, Planck-sized black holes constantly popping into and out of existence, existing for only the briefest moments before decaying via Hawking radiation. Space-time, at its most fundamental level, might be a sea of these tiny, fizzing black holes, where space and time are in constant turmoil. Before Albert Einstein, we thought of space and time as separate and absolute. But Einstein shattered this view forever, showing that space and time are intrinsically linked in a four-dimensional continuum called spacetime. Einstein revealed that spacetime is a dynamic, flexible fabric. The presence of mass and energy tells this fabric how to curve, and the curvature tells mass and energy how to move. This is the essence of gravity. Clocks on GPS satellites tick slightly faster than clocks on the ground. Engineers must account for this relativistic effect, or our navigation systems would fail within minutes. Einstein's spacetime shapes our world in profound ways, from the grandest cosmic scales down to the technology in our pockets. In the quantum realm, an electron doesn't have a precise location until we measure it. Instead, it exists in a cloud of possibilities, a wave of probability, describing where it's most likely to be found. This quantum weirdness is perfectly captured by Heisenberg's uncertainty principle. The more you pin down a particle's position, the more uncertain its momentum becomes. And vice versa. This constant underlying jitter is happening everywhere all the time. The empty space in your room is not truly empty. It is a seething soup of quantum fluctuations. John Wheeler's genius was to ask what happens when you apply the rules of the jittery quantum world to the smooth fabric of spacetime. In Newton's classical world, the universe was a giant clockwork machine, unfolding along a single predetermined path. Quantum mechanics completely overthrew this deterministic worldview. The wave function describes all possible places a particle could be and the likelihood of finding it at each location. Before measurement, the particle is in all possible states at once, a condition known as superposition. In quantum gravity, the universe would not have a single, well-defined spacetime curvature. Instead, it would exist in a superposition of all possible spacetime geometries. The smooth spacetime we perceive would be just the most probable outcome, the peak of a grand cosmic probability distribution. The place where the smooth world of general relativity and the jittery world of quantum mechanics are forced to confront each other is at the Planck scale, the ultimate frontier, the resolution limit of reality itself. To observe a region at the Planck length, you would need enormous energy, but this energy would create a black hole that swallows your probe. The laws of physics themselves conspire against us. What exists is a dynamic interacting foam where observer observed and stage dissolve into a unified quantum system. This is where quantum foam finds its home. The foam is not made of water or soap, but of pure geometry, of space-time itself, constantly fluctuating. Quantum foam takes the elegant picture of smooth space and shatters it completely. If we could zoom in to the Planck scale, the very idea of smooth continuous space would cease to exist. The glass is revealed to be a turbulent, chaotic, ever-changing sea of pure geometry. The breakdown of smoothness challenges one of physics' most fundamental assumptions. Most physical laws depend on infinitesimally small changes, but if space-time has a minimum pixel size, these equations may no longer apply. It suggests that space is an emergent phenomenon, arising on average from underlying quantum foam chaos, much like a smooth lake surface emerges from chaotic molecular motion. We experience time as a constant, forward-flowing river, the steady beat of the cosmic drum marching from past through present into future. If quantum foam causes space-time curvature to fluctuate wildly, then the flow of time itself must also fluctuate. At the Planck time, the steady tick-tock would dissolve into chaotic, probabilistic fizz. This uncertainty in time has profound consequences for causality. In quantum foam, where event sequences can become jumbled, the reliable chain of cause and effect might break down. Perhaps time is not fundamental, but an emergent property of a deeper, timeless reality. The forward-flowing river we experience emerging from the statistical mechanics of the foam. Wheeler imagined that violent energy fluctuations could constantly tear tiny rips in space-time, creating microscopic wormholes, Planck-sized tunnels flickering in and out of existence. This would weave the entire universe together into a single, intricately connected network, at its most fundamental level, providing a physical mechanism for quantum non-locality. If every point is potentially connected through micro-wormholes, then distance becomes much more fluid. The universe might be simultaneously vast and incredibly small. Some theories suggest space-time might splinter into countless disconnected fragments. Our universe could be just one bubble that happens to be large and stable enough to support stars, galaxies, and life. According to general relativity, when a massive star collapses, it crushes itself to a point of zero volume and infinite density, the infamous singularity where our best theory simply ceases to make sense. Quantum foam offers a beautiful resolution. The gravitational collapse would be halted at the Planck scale by immense repulsive pressure of space-time fluctuations. The heart of a black hole might be a seething ball of quantum foam, a Planck star of unimaginable density and energy, but finite. As the black hole evaporates via Hawking radiation, this core could eventually rebound, releasing all matter and information back into the universe in a final explosive burst. Let's rewind the cosmic clock as far back as it can go, past galaxy formation, past first stars, all the way back to the Big Bang. What if the Big Bang wasn't the beginning of time, but a transition from a previous state? Perhaps it was a macroscopic fluctuation, a gigantic wave that rose from pre-existing quantum foam. This paints a picture of a potentially eternal cyclical universe. A universe could expand, slow down, collapse in a big crunch, then rebound into a new Big Bang. The Big Bang is less a moment of creation and more a moment of crystallization, where our ordered world emerged from spacetime's turbulent heart. Wheeler speculated that foam might constantly give birth to tiny baby universes. Most would be unstable, popping back out of existence almost instantly. But occasionally a bubble forms that's just right, undergoing rapid inflation and growing to enormous size, becoming a universe like our own. Our universe could be just one successful bubble in an infinite foam of other universes, each potentially with unique physical laws and properties. This provides a stunning explanation for why our universe seems finely tuned for life. If there are countless universes with random constants, we naturally find ourselves in one where conditions allow consciousness to emerge. We began by looking at the smooth, solid stage of our lives. We saw that this perception is a grand illusion. Our perception has been forever altered. The space between things is no longer empty void, but vibrant, active medium. The floor is a statistical miracle, an island of stability in a sea of quantum uncertainty. Quantum foam teaches us that the most fundamental aspect of reality is not order, but beautiful, creative chaos. It is the unseen foundation upon which everything we know is built. A constant reminder that the universe is far stranger and more wonderful than it appears. Quantum foam is more than mind-bending glimpse into reality. It's a crucial signpost toward the greatest prize in physics, a unified theory of quantum gravity. Theories like string theory and loop quantum gravity are leading contenders. Both picture a universe that is fundamentally granular and foamy at its core. Finding experimental evidence is challenging but not impossible. Astronomers search for subtle signatures on light from distant gamma-ray bursts. A successful theory would be the third great revolution in physics, providing a complete story of the cosmos from first moment to ultimate fate. Our exploration ultimately leaves us in a place of profound wonder and humility, showing that we have only begun to scratch the surface. The foam opens up a universe of new questions. If our universe emerged from foam, was it unique, or are we one bubble in a vast multiverse? Could the universe be made not of matter or energy, but of information? Is quantum foam a cosmic computer processing bits that create the illusion of particles and space-time? If time emerges from timeless foam, what does this mean for free will and destiny? Are we actors in a cosmic play written in the probabilistic language of the foam? Quantum foam represents the ultimate frontier. It reminds us the universe does not owe us simplicity. It is wild, strange, and endlessly surprising. The journey to understand it is one of the most exciting adventures in human thought. The foam shows us that the more we learn, the more we realize how much we don't know. And in that vast space of ignorance lies the future of science and our quest to understand our place in the cosmos.